Hello students, welcome to the course Verilog HDL. In the previous two videos, we have gone through the operator types in Verilog HDL, especially used in Dataflow modeling. Okay, so in this video, we will try to summarize all the operators we have gone through, and we will give a operator precedence. Okay, so in how the order it will be taken into evaluation, and then we'll see in one Verilog example. So of an 4:1 multiplexer, which we have seen in gate level modeling using data flow modeling. Okay, and we'll try to give the observation. So how data flow modeling is better. Okay, so high level compared to gate level. Okay, so look at the operators first. Summary. So first type of operators we have studied arithmetic operators. Okay, so and the symbols are shown here, and what actions they will perform or operations they will perform, and the number of operands. Okay, with respect to this table is formed. So star for multiply, hash for this divide, plus for add, minus for subtract, percentage for modulus, and double star for power. Okay, or exponent operator. So here plus and minus can be used as unary operators also, with specifying the sign of the variable or number. Okay, so that is okay. Second class of operators we have gone through is logical operators. So negation, logical negation, which is the unary operator, operates on one operand, and logical and logical or there are the two operands. Okay, so they will result in always a logical 0 or 1 as the result. Next set of operators we have seen relational operators. Okay, so relation like greater than, less than, greater than or equal, less than or equal. Okay, and all these operators works on two operands. Okay, next equality operators. So there are two classes of equality operators are there. So normal, logical equality. Okay, so comparing the equality. Okay, so just if you write one equal, that is means assignment operator, and we are writing expression a equal to b plus c, so that is assignment operator. But when you write two equal, that is equality in Verilog. Okay, and negation one equal is nothing but inequality. Okay, so this is about the first class. Second class here is if you write three equal. Okay, that is case equality operators. That means it is going to compare even the x and z bits also in the uh, variables. Okay, then negation to equal means case inequality, and all these are required two operands. Okay, so this is the equality. So next comes the bitwise operators. Okay, so in bitwise operators you have one unary operator, that is negation, that is nothing but finding the ones complement. So then we have bitwise and bitwise or, bitwise XOR and bitwise XNOR. Okay, and all this requires two operands to um, do operation. Okay, and there is a clear cut difference between bitwise and logical operators. So in logical operators, so it will consider as non-zero and zero. Non-zero it will give logical one answer, zero it will give zero answer. Okay, if zero number. In bitwise case, so it will operate on bit by bit. Okay, on the numbers. If it is 4 bits, so each bit it is going to do the bitwise and or XOR and XNOR operations. Okay, next class of operators are reduction operators. So reduction or reduction XOR and reduction XNOR. Okay, and the speciality here is it requires only one operand. Okay, so there is a clear cut difference here between logical, bitwise and reduction. So logical and bitwise requires two operands, whereas reduction requires only one operand, and its operation is same like bitwise. It will do bit by bit operation, but the result is of only one bit. Okay, so this also we have observed. So next class of operators is shift operators. Again, you have logical shift and arithmetic shift. So if it is not mentioned means, so 2 greater than symbol means right shift, 2 less than symbol means left shift, 3 greater than symbol means arithmetic right shift. That means it will preserve the sign of the moved bit. Okay, and then arithmetic left shift for 3 less than. Okay, and all this requires two operands. Okay. Okay. Next we introduce the concatenation operators. If you want to pad or append, Okay, so the concatenation, it uses two flower bracket and in between comma operator is used. Okay, so the speciality here is it can have any number of operands. Okay, it does not specify 1 2 3 like that, any number, so multiple operands it can use. Similarly, replication in the concatenation, so this is used to replicate the data. Okay, so you have 0 0, it should be called 8, so 0 0 can be replicated 4 times, so that 8 bits are 0. Okay, so such application, so it will use flower bracket, double flower brackets. Oh, inside it will have the operand and outside it will have the number. Okay, how many times it should be replicated, and then a final closing bracket. Okay, so this is the symbol, and it can also works on any number of operands. Okay, that is a specialty. And last class of operators we have seen is conditional operators. So speciality here is it will have 3 operands. That means it has 2 symbols here, one is question mark, another is colon, and it is conditional. It can use it to implement if else statements, 2:1 mux. Okay, like that. So we'll try to learn this in examples. Okay, so this is the class of operators we have in Verilog HDL. So now we see the operator precedence. Okay, if no parentheses are used to separate parts of expressions, Verilog enforces the following precedence. Okay, always brackets have the highest precedence. In case brackets are not there, parentheses, then it should follow some rule to precedence. So they are listed here. Operators listed in table below are in order from highest precedence to lowest precedence. Okay, and it is recommended that parentheses be used to separate expressions except in case of unary operators or when there is no ambiguity. Okay, wherever you feel like ambiguity is there, you can use freely the parenthesis. Okay, fine. So this is the operator precedence table, so you need to follow. Okay, so unary will have the highest precedence. Okay, like plus minus as used with single operand. Okay, and this is the logical negation, and this is the bitwise negation, right? So only 4 operators you have in unary, so it will have the highest precedence. Okay, as Bodmer's rule you had in algebra. Okay, same like it will be extended. So next comes the multiply, divide and modulus. So it will have the next highest precedence. Then add, subtract will come next. Okay, after that shift operations will come. Okay, so less than, greater than. Then relational operators will come, less than or equal to, greater than or equal to. Okay, and then equality operators are there. Okay, so there are 4 operators are there. Again, it can be used in any level. Okay, so anyone. Okay, all will not be present in all the statement. Then reduction operators will get the precedence. Okay, and then logical operators will get the precedence. Okay, if you have to predict the output of some statement, okay, so you need to know this precedence. Okay, otherwise the compilers are designed, Verilog compilers are designed in this manner. If you give the expression as a Verilog description in data flow modeling, so in this order it is going to evaluate it. Okay, that's why normally brackets are used if you have any ambiguity. And the last conditional, it is a ternary operator, it has the lowest precedence. If it is there, it will be evaluated at the end. Okay, so this is the operator precedence table. You can pause and go through in detail. Okay, you can note down. So fine, so with this, we are completing the theoretical part of this data flow modeling unit 6 of module 3. Okay, so now we have set of examples. Okay, so some examples of previous unit, they will be modified here using their Boolean expressions. Okay, and some of the new examples we are going to see. Okay, and after that we'll see the exercises. Okay, so before that, so the concept of these operators. Okay, assignment statement, delay, how we specify. Okay, so if you have not gone through, so I suggest you to please go through that, and then you can come back and continue with this video. Okay, fine. So these are the set of examples we are going to discuss in this data flow modeling. So first I will be considering the same example. Okay, so this is the example we have seen in gate level modeling, 4:1 multiplexer. Okay, so what was the procedure? If you recall, I told you I won't tell you to by heart. Okay, there is a clear cut step is there. So we need to write logic symbol or IO diagram. Okay, then you write the truth table from that. then you write the K map and Boolean expression, then gate level diagram. Okay, so gate level diagram, there is a one-to-one correspondence with Verilog description. Okay, so once you write the primitive gates you have called, then you are writing the stimulus module, and then finally you will see the simulation output. So these are the 7 steps we have followed. So now in this model, data flow modeling, this step is going to be removed. Okay, which is that step, the 4th step, which is gate level circuit. We are not going to draw this. Okay, because it is a data flow modeling, so we are going to do the Boolean expression too. Okay, so this step is not there completely, and here a new description will come. Okay, so gate level instances you used to use, now we are going to use the assign statement with the expression. Okay, so that is a specialty. So logic symbol will be there same, truth table will be same, and then Boolean expression. So this Boolean expression to this, there is a one-to-one correspondence now. Data flow modeling. Okay, so we are going one step higher now. Okay, we are going one step higher. That's why we are not taking gate level diagram and this description. So we are going to Boolean expression level, and that corresponding description we are going to explain. And then stimulus module and these things are same, simulation output, because these things won't change, right? Design won't change, only the module internally how they are working, that is going to change. Okay, and this is possible only because of the logic synthesis tool. Okay, I mentioned there is a logic synthesis in the very first module in the this one, evolution of CAD tools, only mentioned this, right? So because of this logical synthesis tool, we are going to do the design at RTL level. And what is RTL level? It is a combination of data flow and behavioral level. Okay, so why it is RTL? So here some of the cases you may get the Boolean expression, like you have multiplexer, now adder. Okay, all these will have expression, but some of the cases you don't have the proper Boolean expression. For example, if you have to model a traffic signal controller, okay, in that case there is no clear cut Boolean expression, then we have to go for behavioral description one step further with algorithm, right? So that's why these two levels, what is that level, data flow and behavioral level, are called as the RTL description. Okay, so we'll see that part again. So now what we are going to learn in this module is these two we'll going to see first. Okay, and there are two ways are there. One is straight away logic equation, that is a Boolean expression. Another one is conditional operators. So we have learned conditional operators. Using that also we can model the 4 to 1 multiplexer. And then 4-bit full adder also we have seen earlier, so that we write using now simple logical equation in a single line. So this also we are going to see, and these three we have done already. So that's why stimulus model and our simulation output I am not going through, only the first 3 steps and the Verilog description in data flow I will show you. Stimulus module you can copy same from the previous one. Okay, so that is the idea. Fine. So then full adder, 4-bit full adder with carry locate. So these are the two new programs we are going to learn here. It based on completely Boolean expressions. Okay. So that's why these two new things we are going to learn. So next 3 to 4 videos we'll be discussing completely regarding these examples one by one. Okay. So for today, I'm going to focus on this 4 to 1 multiplexer using logic equations. Clear? Okay. Okay, so 4 to 1 multiplexer using logic equations. Okay, so some theory before I start with the actual design. We can use assignment statements here. Okay, assign keyword is the funda for data flow modeling. Instead of gates, to model the logic equations of the multiplexer. That's why I told you till logic equations or Boolean expressions I will write the design. Then straight away it is having one-to-one correspondence with data flow modeling, which is nothing but assignment statements. Okay, we call everything here assignment statements. Clear? Notice that everything is same as the gate level Verilog description, except that computation of out is done by specifying one logic equation, okay, by using operators instead of individual gate instantiations. Previously for multiplexer design you written some set of primitives, right, 3 to 4 line or maybe more than that for complex circuits. Okay, but here it can be done using a single expression in a single line. Okay, so that is the speciality. Okay, so the logic synthesis tool will convert this into a gate level design. Okay, whatever you have written previous module, so same level it is going to carry out. Okay, but you are not going to design at that level, because designing at that level is very tedious now and time consuming. Okay, so we need to reduce the time to market. Okay, so we have to design the circuits very fast. That's why these techniques have come. Okay, so we are going to learn these techniques here. IO ports remain the same. Okay, so since the design is not going to change, internally only we are changing. That's why whatever you are writing first part, input output declaration, list of ports, everything is same. Okay, that's why I have taken the previous example only first to show this difference. Okay, this is important so that the interface with the environment does not change. Okay, this is does not change, only the internals of the module will change. Okay, so notice how concise the description is compared to the gate level description. So this is what the observation you have to do at the end. How concise the statements are, very less. Okay, and it is concise description compared to elaborated gate level description. Okay, in gate level you has the logic diagram, and each diagram, whatever gates you have used, you used to call that instances. Now it is not the case, just expression you are writing with the help of operators. Okay, so just same thing I am repeated here. So 4 to 1 multiplexer using logic equation. As I told you, very first step is IO diagram. Okay, the first step is IO diagram. You no need to by heart here again. So write the IO port diagram, or it is called as logic symbol. What is 4 to 1 mux? Its output is only one. It should select multiple input lines. Okay, based on the select lines. For 4 to 1 multiplexer, as the name mentioned, which is 2 to the power 2 to 1. Okay, 2 to the power 2 to 1 means what? It should have two select lines for four combination of inputs. Okay, the inputs are named as IO, I1, I2 and I3, and the two select lines are S1 and S0 is given. And so based on the S1 and S0 values, the corresponding inputs are selected. And as I mentioned, the best example is your TV remote. Okay, or your FM. If you are using FM stations, there are multiple stations are there, but at the time you are going to see only one station. Okay, so that is how these multiplexers. So these are very simple we are discussing here. In actual cases it will be 16 marks, 32:1 marks, 64, 128, 256, 512, 1024, like that. Very big marks they will design. Okay, fine. So based on the input, 0 0 means I0 is selected, 0 1 means I1 is selected, 1 0 means I2 is selected, 1 1 is I3 is selected. So this is very important, because we can change this pattern also. Okay, so how we have taken in the design, accordingly program will come, and the same thing you will tell you to your clients. Okay, so now 0 0 I can model it I3 also, 0 1 I can model I2 also, 1 0 I can model I1 also, 1 1 I can model I0 also. Okay, it all depends on how you have designed. That's why we are going to write this in the very beginning. Okay, how I have modeled. Okay, there is clear cut with the names, everything. It is one to one correspondence will be there. Okay, so now we'll write the Boolean expression for this. So 0 0 means S1 bar, S0 bar, I0. Then we have to add this, right? Plus S1 bar. So in the sum of products, 1 means as it is, 0 means complement will take, right? So S1 bar, S0, I1. So three input AND gates we used to have right there. Now we'll see how it is. One line we are going to finish it. Then 1 0 I2. That means S1 S0 bar I2. Okay. Then S1 S0 I3. Okay. So I3 can have any value again, 0 or 1. Okay. Fine. So this is the expression, whatever I told you then, that is written over here. Out is equal to this we have seen in previous case also. S1 bar S0 bar I0, S1 bar S0 I1, S1 S0 bar I2, S1 S0 I3. Okay. So this is the logic equation. So this is the program now, a new program for you, or new level description. Okay, so the first part is same. Okay, so if you compare this, so module name is given, so give some name, it is same. Then list of ports what you have used, same. Out, I0, I1, I2, I3, S1, S0. All the inputs and outputs are mentioned here. Then there is a clear cut classification. Okay, so output out. Okay, input is I0, I1, I2, I3, and input S1, S0. Though this is the part same you have seen, just you can compare This is not going to change. What you are going to change is next. Okay, here what you used to do in the internal, okay, the architecture part or the relationship between inputs and outputs, we used to use gate level model, right? Now we are going to write the logic equation. Whatever Boolean expression I have written, that I am using operators now to design that. Okay, and all this is single line. Okay, so just to show you, it is written in multiple lines and there is no problem for that. Okay, so s1 bar, s0 bar, I0 was there. So that is the way we are writing in Boolean algebra. But in Verilog description, we used to use operators. S1 bar means what? It is one's complement. So we'll use bitwise negation. Okay, not logical, bitwise. Okay, careful. Okay, so not of S1, not of S0. That's why operators are mentioned here and I0. So these are the three. Okay, first these not are done, then and we have used. Okay, so even if you are problem with, so here unary is having the highest precedence. That's why brackets are not put. In case you can put one more brackets also for not of S1 and not of S0. So no issues. Brackets will have the highest precedence. But here with respect to and this, so this will have the highest precedence because unary. Okay, fine. Not of S1 and not of S0 and I0. And is for here single and is used, meaning what? Bitwise and there are three operands are there, two or three operands are there. So that's why it is not a reduction or and. Okay, so from this it is going to, and this is the symbol for plus, right? Or. Okay, so there is a or symbol, it is there in your keyboard. Whatever is there in your keyboard only, the names are selected here. Okay, operator symbols are selected. Okay, then s1 bar, s0, I1 you have. Okay, so only s1 you have to do negation, s0 as it is, and I1 and you have used, then or. Okay, so this is completely a single line. Okay, so just for simplicity I have shown like this. Okay, in the first example, then you have s1, s0 bar, I2, right? So s1 as it is you are writing and negation we are using for s0 now. Okay, so this is how written third statement, and finally all are one. So s1, s0, I3. Okay, so after the end of the statement we are writing the semicolon. So this is completely a single line. So whatever you are, so just you can compare now, go back and compare your, if you have written down multiplexer, how many gates we have used for this. So we have used the two NOT gates first for S1 and S0. Then we have used four 3 input AND gates. Clear? And then one 4 input OR gate, right? So this is the design. Okay, we have used in gate level modeling, but now we are using a single expression with the help of operators. So when you run this in a CAD tool, so it will have a logic synthesis tool which will convert this into a Verilog gate level model. Okay, so at the lowest level it is going to take that, but the user or a designer, as a circuit designer, we are not going to do that. Okay, so we are writing the program now at data flow model. That's why I have not taken in reverse manner. If I have shown behavioral first and then data flow, you will not interested in learning this. And if I show data flow first and then data level, so you'll feel like, sir, this is easy compared to that. That's why we are going in reverse manner learning this. Okay, so gate level is a complex if you have a large circuit. Okay, so that's why we have taken this data flow modeling now. Okay, so we'll try to go through my more examples in the coming videos. Okay, fine. So the stimulus module and simulation output is an exercise for you. It is exact copy of whatever you have done, because there is no change there. Only here this design is changed. In the stimulus module, only one thing you have to change is if this name is changed. If the module name is changed, that only you have to change it there. Otherwise everything is same to same. Okay, fine. Okay, so we'll see in the next video. Okay, we'll go through this.